I am Will. My teammates are Tasha, Brock, and Ben. And this is our physics video. For our physics project, we spun Ben around in a hammock many times, and it usually resulted in swinging him into the ground, but one time it succeeded. So we used that to calculate some things about the hammock, so Tasha will explain that next.
Okay, so before we get to Tasha, this is a video of me going around, making one full rotation, and what we basically did is we put this video, well, a video similar to this, into Tracker from a different angle, and we started up at the left, and we tracked my frames going all the way around. So we got the initial frame at this point right here, slowed down, and then we go all the way around to that same point again, and that's our final frame, and we use that to calculate our time, which Tasha will explain. So here's Tasha explaining it, then we're going to have Brock explain why it makes sense, and me explaining the lenses.
Hey class, here is our calculation of Ben spinning in the hammock. To start out, we found out how long it took him to make a full rotation. And to do that, we found what the first frame was when he starts his spin, which is at 103, and his final frame was 150. So the total rotation was 47 frames. So for our calculation, we found that 2 pi, which is one circle, was 47 frames divided by the 228 frames of the whole video. And then we multiplied that by 7 seconds because that was the time of our total video. And we found out that one rotation took 1.44 seconds to make. And then we took that for our calculations over here. So the radius of the circle he made was 0.9 meters. And his mass, Ben's mass, M of B, was 57 kilos. So our first calculation, we found omega, which is the change in theta over the change in time. To find that, we did 2 pi over 1.44 seconds, which was 4.36 radians per second. Then we found the average linear velocity, which is omega times r, or 4.36 radians per second, times 0.9 meters, which was 3.924 meters per second. Last, we found the centripetal acceleration, which is v squared divided by radius. So we found the square of 3.924 meters per second over 0.9 meters, which was 17.11 meters per second squared, to find the centripetal acceleration.
What's up, class? Alright, so as you saw in the video, we were able to succeed one time in completing one full rotation without losing Ben from the hammock. And so we calculated that our centripetal acceleration was 17.11 meters per second squared, which is greater than the acceleration of gravity pushing down on Ben when he's at the top of his rotation. So it makes sense that he was able to stay in the hammock.
The lenses for this problem, we can look at 2 different lenses, and initially we would be looking at a kinematics lens because we are looking at our angular velocity, which we calculated using the change of theta over the change of time. And then from there, we could calculate our linear velocity, and we use omega times the radius. And from there, we can calculate our centripetal acceleration, and that would be our kinematics lens. Then if we wanted to expand on the problem and find a normal force, we could use a dynamics protocol, and we could use the sum of the forces equals mass times acceleration to calculate our normal force. And basically what the normal force is in this situation is the hammock would be giving us our normal force, and the normal force in this situation is basically the hammock preventing me from flying straight up when they rotate me in the hammock, and that would be a basic version of the dynamics lens.